Okay, it's a great pleasure to be here in Nordita in this beautiful city, and at this occasion on for discussions of Hawking radiation. My talk is not directly about anything time dependent, I have to admit from the start, but perhaps it does fit into the general context of some of the things discussed in this conference. Most recently, the main work I'm going to tell you about relates to two recent papers together with my student Alan Perkins and with Hong Lu and Chris Pope. But it also goes back to issues that have been of concern to me for a long time, back from the 1970s. So it's about what happens when you include higher derivative terms in the gravitational action, specifically quadratic terms. So I'll just begin with a little bit of scene setting here. The Weil squared and R squared terms do arise, as Gerhard and Tini Veltman showed in a classic paper, as the divergences in general relativity at the one-loop level. And if you include those in the gravitational action ab initio, as I showed back in the 1970s, you obtain a renormalizable theory in 4 dimensions. But there's a price to be paid, which is a loss of unitarity, which I'll come to in more detail later on. This arises specifically from the Weil squared term, which, however, is essential to have the renormalizability property. C mu nu rho sigma here is the Weil tensor. You can also reparameterize this if you wish in terms of r mu nu squared minus a third r squared, which via the Gauss-Bonnet theorem is equivalent to the Weil squared term. Now, these types of theories have been considered in a number of recent contexts, and indeed, Gerhard began the first talk in this conference with exactly taking the direction of such theories. Let me mention also the model for inflation that Alexei Starobinsky has put forward, and according to the month or the week, is sometimes in favor, sometimes out, depending upon the observational situation. Another point of view, this, however, I will mention because it gives you an idea, perhaps, of what some of the coefficients might be in the action. I had these alpha and beta coefficients. So this gives you a definite value, at least for the R squared coefficient, which is rather large. Now, another point of view on such terms has been it derives from ideas of Steven Weinberg and has been pursued by Reuter and Niedermeyer and many others, the asymptotic safety scenario, which addresses the problem of the ghosts, really, by saying that although, first of all, there may be a non-Gaussian renormalization group fixed point for this renormalizable theory, may in fact limit to a non-Gaussian fixed point at large momenta, and it could be associated flow trajectories on which the ghost states might be absent. This also relates to an early result of Fradkin and Saitlin, that the Weil squared and R squared terms are not only renormalizable but also asymptotically free. So it's possible that if you choose the right renormalization group trajectory, the coupling to in particular the spin 2 massive ghost states could be such that they're not excited along a certain trajectory. Well, I'm not going to go into these debates. One can argue back and forth about whether it's sensible to take a theory like this and consider it as a quantum theory. I'm just going to explore the solution space of such a theory, and I'm going to stop at the curvature squared terms, basically for the reason that we've been able to say something about this theory, and it becomes much harder to go beyond that. But there are also, because of the renormalizability, there are perhaps arguments for considering this as a theory that has at least some domain of validity before you perhaps get involved in yet higher curvature corrections that you'd have to deal with. But there could be ranges of momenta and energies where this is the relevant effective action. Now, if you vary that action, you obtain the following field equations, which I've called h mu nu here. Of course, you start with the ordinary Einstein field equations, and then you have the consequences with alphas and betas coming from the Weil squared and R squared terms of the higher derivative terms. And I've put, for sake of discussion, a T mu nu on the right-hand side here if you have this coupled to ordinary matter system. The renormalizable system, by the way, will be this action that I've shown you plus ordinary matter, the standard model. You don't have to put higher derivatives into the matter sector. The matter sector, renormalizable in flat space, plus the higher derivative theory that I've given you, that makes a renormalizable system. So this T mu nu could very well be an ordinary type of T mu nu from Yang-Mills. Now, when you vary the field equations, first of all, we're going to be looking for spherically symmetric solutions. So in this talk, I'm going to consider it in Schwarzschild coordinates. There are debates about whether this was the best choice. Relativists come and say maybe there are more clever ways that can decrease some of your eventually numerical difficulties. And indeed, I'm very open to suggestions along the lines of perhaps organizing this better. When you vary the action, you can, because this is, by the way, an imposition of a symmetry in the ansatz of the solution, it corresponds to a consistent truncation. So one way to derive these equations is actually to insert this expression for the metric into the action, write the action in terms of A's and B's and so forth. The B here is the time-time component, the A is the space-space component, and you obtain an action written in terms of A's and B's, and then they will derive the same equations here. The equations are ugly. I'm not going to go into any detail. I merely want to point out one thing. Because of the gauge invariance of the theory, the Bianchi identity, you know from the start that you're going to get one field equation of one order less than the maximum here, which is 4. And then you're going to get another field equation which is 4th order in radial derivatives here. So we're just considering time independent solutions. However, given that 3rd order equation and the 4th order equation, what you can do is you take the derivative of the 3rd order equation and you combine it with the other equation. You can remove the highest derivative also from the other equation. This gives rise to what's on the next slide, a bit ugly, but the point is that you have 2 equations with the highest derivative order being 3rd. So that gives you already a piece of information about the solution space. You should anticipate 6 integration constants from this set of equations. They're highly nonlinear and rather ugly, and it's not going to be very possible to obtain a closed form solution of this, but we're going to try to do the best we can. So in order to get the 3rd order equation, you also have to take a particular combination of the field equations, the TT, RR, and derivative of the RR equations in order to make this come out. But you can boil it down to a set of 2 3rd order ugly nonlinear interacting differential equations. That's the end of the free lunch. From here on, you're going to have to work with this system. Now, in order to understand this a little bit better, it's useful to retreat to the linearized theory. And I just want to show you now a little bit more in detail what the modes are. So if we make the standard expansion of flat space plus h mu nu here, and then look at the action at the quadratic level in fields which will give rise to linearized field equations, the action can be reduced to the following expression involving spin 2 and spin 0 projection operators. And you can see that the alpha coefficient here relates to the spin 2 part, the beta coefficient here relates to the spin 0 part, and then the terms, of course, you have box here, those are the 4th order terms, and then terms which are purely 2nd order, with the gamma coefficient comes from the ordinary Einstein term in the action. So from that, you can see what the dynamical content of the theory is going to be. You have ordinary massless spin 2, which providing you've put the correct overall sign for the action will be positive energy, positive metric, massless spin 2. Then you have massive spin 2 as well, as you can see from that spin 2 projector, which however is negative energy, and Gerhard introduced the term gravitello for it. I looked in Italian dictionary. Gravitello actually does have a meaning, and we can debate whether this is instructive or not. It's actually a floating buoy to tie your boat to. So Then you also have a third mode here, which is, because of the spin 0 part, it's massive spin 2, and so here the spin 0, excuse me, here the spin 2 mass and the spin 0 mass, depending upon alpha and beta, and that's a positive energy. So note that if you have just the r plus r squared terms, there are no negative energy problems. However, it's not renormalizable, but that is exactly the starting point for the Starobinsky inflation model, without any negative energy modes. Okay, so that was an introduction about the linearized theory. Now, if you go further and try to find static spherically symmetric solutions to the linearized theory, as I've said, you're going to anticipate 6 integration constants, and here I've given them names. This is still for the linearized theory. And here are the solutions for the A, that's the GRR, and B, that's minus GTT functions here. So you see the 6 integration constants come up. You have the parts, the C and the C20, these are the parts that you'd see in the Einstein theory. And then you have Yukawa terms, as you anticipate from the exchange of massive modes, spin 2 and spin 0, with rising and falling Yukawa terms. So in order to talk about asymptotically flat solutions, you're going to have to impose boundary conditions at infinity to kill off the rising Yukawas in the A and the B. So that means turning off the C2 plus and C0 plus coefficients. Now, so we've seen we have a 1 over r potential plus the rising and falling Yukawas. That's for a generic solution with no stated stress tensor on the right-hand side. But as in Einstein theory, when you put a specific stress tensor on the right-hand side, of course, you're going to determine, together with the boundary conditions at infinity, you're going to determine the values of those coefficients. So if in the linearized theory, it's safe enough to put a simple point delta function source with a mass m. So here I've given you a t mu nu, which is just delta mu 0, delta nu 0 times m times the delta function at the origin. It's dangerous to do this in the full nonlinear theory, as we know from the work of Garrosh and Trashin. I'll come back to that in a moment, but in the linearized theory, it's fine. And you obtain the following expressions. I've killed the spin 2 and spin 0 rising Yukawas at infinity, and here you can see that the remaining coefficients are now determined in terms of the parameter of the source. Now, that's for a simple point delta function. In general relativity, you have the nice feature, because of Birkhoff's theorem, that once you've solved this problem, you actually have the general solution as well. That's not the case here, however, because there is no Birkhoff theorem in this higher derivative theory. So if instead of this simple point delta function source, you take a more complicated source, for example, the child's balloon with a gas, pressure, and an overall mass density, and some sort of rubberized source in order to constrain it, you need to have a boundary with a delta function in order to hold it in and make the stress tensor be conserved. And so I've given here an example of such a stress tensor. Then the result, for example, for the B function is as follows. You see, again, we're determining the parameters of the 6 minus 2 that are killed by boundary conditions, parameters in terms of the source, and also a boundary condition setting B to go to 1 at infinity. Remember, there's another feature of all of these theories, that the time component can be adjusted by simple rescalings. And so that's essentially a trivial component. In other words, you want the GTT component to go to 1 at infinity. And so that's another normalization condition at infinity that you'll impose, and it's been done here to set this coefficient to 1. Then you have the Yukawa terms with coefficients here that depend upon the parameters of the source, the size of the source, the mass parameter of the source, the pressure, etc. So just to emphasize that there is no Birkhoff theorem, and the details of what you get depend upon the details of the source that you propose to couple on here. If you take the limit of this balloon as the size of the source L goes to 0, it reduces back to the point construction I had on the previous slide. Okay, so that was the linearized theory, and that's pretty clean. You can do that. Now, to confront the full nonlinear theory, we're going to have to approach it in two fashions. The linearized theory is relevant if you talk about asymptotically flat solutions. As you get far enough out to infinity, everything I've just told you about the linearized theory is still relevant. But you're going to have to now couple it on to something that happens deeper into the solution. And you have to identify the types of behavior that you can see. So let's look at the origin, r equals 0, and make a Frobenius analysis. This is what's called solving the indicial equation. So you make a Laurent series expansion with an unknown initial power s for the a coefficient and t for the b coefficient. These don't have to be integers. They can be whatever come out from the analysis. And here's what you find for the leading powers s and t. There are three families here. 1 minus 1, by the way, this is where I should mention right away that every solution of Einstein's theory, r mu nu equals 0, is also a solution of this theory. If you go back to the field equations, the full nonlinear field equations that I showed you, there's an r mu nu in every term. So if r mu nu equals 0, it automatically satisfies the full nonlinear field equations. And the Schwarzschild solution is in there as well, and it lives in this family. There are two other families, however. One where the metric goes to 0, goes to a constant at the origin, and one where it goes to 0, like r squared, both in the space and time components of the metric. Were this a linear theory, there would be general theorems that you could employ to declare that you know these behaviors from ab initio. And well, Carl Bender comes around to visit us a lot in London, and he loves to terrify me about things that can happen in nonlinear theories. So there are no general theorems about the indicial behavior that can happen here. All I can say is we've tried all of the other types of behavior aside from these, for example, with logarithms, with Yukawa type terms included in the starting thing, and this is all we've found. So we've analyzed this basically by exhaustion of us and anything we can think of for the leading behaviors. So this seems to be the result. So at the origin, these are three families, and the count of parameters we've also done. Now, counting the parameters correctly is something I started doing this back in the 1970s by hand. In order to get it right, one really needs algebraic computational methods, because the way, for example, the 6 parameters come up here, you have to go out to something like 9th order before you find the last free parameter. But those families and their number of free parameters is going to be rather important for issues of coupling. Now, I've showed you what happens when you put a delta function into the linear theory. Now let's try to consider the same question in the nonlinear theory. So I don't want to try to put a point delta function in the nonlinear theory, because that's known to produce difficulties in general relativity. What we can do instead is basically put an eggshell. It's a delta function of mass distributed spherically symmetrically around the origin at some distance, some radius epsilon. So this will be codimension 1. And from the work of Garrosh and Trashin, we know that that type of distributional source is the one that can couple sensibly to nonlinear theories like general relativity. Outside, we're going to consider the three families, three types of behavior that I just told you about, the 1 minus 1, 0, 0, 2, 2. Inside, we don't want to have any more sources. We're putting the source at a radius epsilon, so inside it has to really be, quote, the vacuum. Now the vacuum will be a type of solution that doesn't require any source at all. Well, in fact, that is what the 0, 0 family is. It's non-singular solution. The metric, and both components of the metric go to constants, and in fact you can convince yourself that it doesn't require any source. So that is the analog of flat space for the same construction in general relativity. Now suppose outside we had one of the 2-2 solutions, and remember the parameter count. So if we have 0, 0 inside, I told you on the previous slide that there are 3 parameters there. Outside there's 6 parameters, so that's a total of 9. But now you have to do the Israel type discussions, their continuity and jump conditions as you go across this source. You have to integrate the field equations across the source, and there are 6 continuity and jump conditions coming from the field equations. So you really have 9 minus 6, that's 3 parameters that are still free, but this is all talking about the behavior at the origin, and it's going to evolve as you go away from the origin to something at infinity, and we want to talk about solutions that are asymptotically flat and with the GTT normalized. Those are exactly 3 conditions at infinity, which you will use up these 3 parameters that you still have available to you in the expansion around the origin. Some combinations of those are going to be necessary to arrange the type of solution, asymptotically flat solution you want at infinity. The point about this is it works perfectly for this 2-2 family, and it doesn't work at all for the 1 minus 1 or 0, 0 solutions. If you try to have them as the exterior solutions outside your distributional source, there are not enough parameters in those families to match. One can also go through an analogous discussion, for example, in a higher derivative scalar theory. You see that the 1 over r solution to box phi equals 0 is a good solution of box phi plus box phi, but it's not the one that couples properly to a delta function. One that couples properly to a delta function is not the ordinary 1 over r. And so in this case, the Schwarzschild solution, which is of the 1-1 type, is a good solution if you ignore issues of sources, but it's not the one that will couple properly to this distributional source. So the distributional sources seem to require that you fall into this 2-2 family at the origin, and that will have further implications for what I want to tell you later on. Okay, now to try to bridge the gap between the origin and infinity, well, one way is just to try to calculate, and that's just confronting those equations is hard. However, we have a piece of luck. There is the remnant of an OHara theorem that is still useful here. Now, if you take this actually derives from a paper by William Nelson, who's at Penn State. We agree with half of his paper. And I'll tell you that half right now. By the way, I'm only going to consider the 2 masses in this theory, the spin 0 and spin 2 mass. I'm considering the non-tachyonic signs of those masses. I'm not going to talk about anything else. So if you take the trace of the field equations, you get this, which is box minus gamma over 6 beta r equals 0. So it's a Klein-Gordon equation for the Ricci scalar. Lambda, we're considering static solutions which have a time-like killing vector, of course, which is orthogonal to a spatial slice. So lambda is the norm squared of the time-like killing vector. So if you multiply by lambda to the 1/2 times r and then integrate over a 3-dimensional spatial slice at fixed time, you obtain the following expression. So I've started with the field equation, with the trace of the field equation, and this is now all integrated equal to 0. The first term here is a total derivative. So this is the usual pattern of a no-Hare theorem. The second and third terms are squares and of the same sign. They're both negative in this case. So providing we can ignore the effects of the total derivative term, at infinity this will be straightforward because we're going to talk about asymptotically flat solutions. And if we start at a horizon, at an inner integration surface, that first term will also be gone because the lambda is the norm of the time-like killing vector. So if we go from a horizon to asymptotically flat infinity, we obtain an integrated sum of squares, one of which is r squared, equals 0. So therefore, you conclude that the Ricci scalar has to vanish for any asymptotically flat solution with a horizon. This immediately means that if you have the spin 0 Yukawa term present in a solution, that's fine. There are solutions like that, but that solution is not going to have a horizon. Okay, so that's really just the point I've made here, that if you have this spin 0 Yukawa asymptotically out at infinity, there are solutions like that, but they're not solutions with the horizons. They're not ordinary black holes. What about the non-trace part of the field equation and the corresponding spin 2 Yukawa corrections? Well, what Nelson's paper would have told you would have been great, and this would have been a very easy, short discussion. He claimed that you get the same type of construction with sums of squares of the same sign, integrated equal to 0. Unfortunately, there's sign errors in the paper, and when you do it carefully, you see there's sums of squares of alternating signs, so you lose the non-trace no-hair theorem. But you do have the trace no-hair theorem, and that makes already quite a lot of progress. So we're now going to focus on solutions. If we're interested in solutions that have a horizon, we now have learned that R has to equal 0. And if you count parameters again, now you do similar Frobenius expansion, not around the origin, but around the horizon. And you'll find that subject to the R equals 0 condition, you now have 3 parameters, similar to the counts that I did around the origin, but now subject to R equals 0, you have three parameters on a horizon. So asymptotically flat solutions with a horizon must belong uniquely to this 1 minus 1 family, which, by the way, contains Schwarzschild, as I've said. And Schwarzschild itself has 2 free parameters. One is the mass of the black hole, and the other is this trivial parameter corresponding to GTT, which can be set to a constant at infinity, but you normalize it to 1. But that's a trivial parameter that can be adjusted by rescaling. So it's Schwarzschild 2, and this family has 3. So there's 1 non-Schwarzschild parameter in this family of solutions. There's 1 knob to turn away from Schwarzschild, and only 1 knob. Okay. Well, so that already gives a picture about what could be happening more generally. If you start at Schwarzschild and try playing this knob a little bit, you can see pretty much what's going to happen. As soon as you turn it away from Schwarzschild a little bit, something has to happen. It's no longer Schwarzschild. But when you turn this knob, there's one condition at infinity was needed to keep the rising exponential killed off. As soon as you turn this parameter, you're going to cause the rising exponential at infinity to come back on. So this is telling you intuitively that the Schwarzschild solution generically is going to be isolated. As soon as you go away from it a little bit, you will break the asymptotic flatness condition at infinity. Now, we can say this in a rather more precise fashion by, again, going back to no-hair theorems. Not, in fact, for the non-trace part of the field equations, I've just told you that you can't get a generalized no-hair theorem for the non-trace part of the field equations. But what you can do is you go away from Schwarzschild, you linearize in the deviation from Schwarzschild, and you now derive a no-hair theorem for the linearized deviation from Schwarzschild. And you conclude similarly that for spin 2 masses that are not too small, or coefficients alpha that are not too large, you do have this linearized no-hair theorem that says that the Schwarzschild solution is isolated as an asymptotically flat solution with a horizon. There are all of these qualifications, however, which probably make you wonder, is there more to this story? Suppose you go away from Schwarzschild within this 1-parameter family of solutions containing Schwarzschild. If you go a long way away, is there something else that you can't discover by just looking infinitesimally close to the Schwarzschild solution? Well, that's what we call non-Schwarzschild black holes. So as you move some finite distance away from Schwarzschild, you first of all lose asymptotic flatness, but it could be that as you continue turning this 1 knob, that eventually you reach another solution where asymptotic flatness comes back. Now, the only way we can see to answer this is numerically. So we've basically using shooting techniques, we analyze this. And in fact, we find that there are such solutions. Because we're dealing with Ricci scalar equals 0, as I've explained, for assuming we're looking for solutions that are asymptotically flat at infinity and that have horizons, this means we can effectively concentrate on the theory with just the R and the Weil squared term. That gives us another nice Christmas present. You can reduce the order of equations. Instead of third and third, you can reduce it to second and second. It makes the integration much more feasible, the numerical integration much more feasible. They're still a bit ugly, but they are, in fact, reduced to second-order differential equations. Here's the way we parameterize things. Again, with B, for the GTT, let the A coefficient be called 1 over F now. And we can first of all do a similar expansion around the horizon for B and F. And what we find is that because we're talking about a horizon, the B coefficient goes to 0. The B function goes to 0, because that's what we're discussing, at some radius r0. And then we find from the study of the equations that F also has to go to 0 similarly linearly. So there are free coefficients C and F1 here, and R0. So those are the three parameters, in terms of which everything higher, the H2, F2, F3, and so forth, those are all by the field equations are determined in terms of these three free parameters. So we know that for Schwarzschild, F1 here is just 1 over R0. So it's convenient to rewrite F1 in this fashion as 1 plus delta over R0 and let this be the non-Schwarzschildality parameter, and then explore what happens as we move around in the parameter space of delta. So what we find is given here. There are asymptotically flat non-Schwarzschild black holes, providing the horizon radius exceeds a certain minimum value, R0 minimum here. So for alpha equals 1/2, that's the coefficient of the Weyl squared term in the action, you find the following sort of picture. So in this case, you can see this value of R0 minimum. So you have another branch. The dotted line here is the Schwarzschild branch, and then a new branch of black holes comes into the solution set. So the isolation of Schwarzschild, of course, is still true, except that there's a point here where it's not isolated, which is the branch point. And indeed, if you study the linearized no-hair theorem, you find the linearized no-hair theorem breaks down at a certain point. So it's actually also telling you that you should have suspected a branch point in the solution. But in general, this is the pattern with a new family of non-Schwarzschild black holes. They are asymptotically flat. They're still in this 1 minus 1 family at the origin, but they are different. So some properties of them. You can see that for this minimum radius, that corresponds because the mass was going down as you went higher and higher. There's a maximum mass is given here, and in terms of the parameters, this is a numerical result, alpha and gamma of the action. We found the maximum mass is given there. So the non-Schwarzschild black hole does have a Yukawa term. It turns out to be with the C2 minus coefficient here, that is the same sign, positive as M. So this happens to be opposite to the sign that you get from the positive energy shell source in the linearized theory, but this is a solution of the full nonlinear theory. It's just what you find. Otherwise, if you look at the evolution of B and F, as you go far out, it approximates to Schwarzschild. And as you come in, they're slightly different, but it is in fact a different solution. The mass, of course, decreases as the radius of the Schwarzschild increases. And another feature of that is you can see that there's a point at which the non-Schwarzschild black hole actually becomes massless. Okay. So this is a new feature, which is just what one finds when studying these solutions. This may be certainly of some concern, but it's what the equations give you. The specific heat, as you can see, is the derivative here is negative for both the Schwarzschild and non-Schwarzschild black holes, and in fact it's more negative for the non-Schwarzschild black hole. Now, that was about the non-Schwarzschild black holes. There are other solutions which I've alluded to. There are other solutions which do seem to be the ones that couple nicely to distributional shell sources. And these are in the 2-2 family. So again, we find these numerically. They were found in an earlier paper by Bob Holdeman in Toronto for the case where the spin 2 and spin 0 masses were set equal, and we did it in the case where we have only the spin 2 mass, the R plus C squared theory. And you have this sort of structure. This is for the log A and log B, minus log A and log B here. So this falls in, you can see, by the way, by the slope here as they're hitting here, that it is in the 2-2 family, going like r squared as you approach the origin. Out at large radii, it has very Newtonian type behavior and in fact asymptotes to the Schwarzschild solution. The Schwarzschild solution as you come in will, however, reach a horizon, and that's where this dotted line branches off. But these two solutions do not have a horizon, and they continue on in without a horizon. So that is another family of solutions that we find in the sort of zoology of solutions in this theory. By the way, so this is in accord with the parameter count, as I've said, for the coupling. Now, another thing I will note about this is that because the space and time components of the metric are going like r squared for this class, that means the curvature actually is singular, and in particular the curvature squared here goes like r to the minus eighth. So this is a solution with a naked singularity, but because there's no horizon, there's no flip of the light cones, this is not what you're used to. This is the time-like singularity. It's more like an electron in electrodynamics. It is. The word graviton has already been used for another purpose, but that is the sort of thing you might think of here. There's another type of solution we find in the theory. Remember, I told you that if the time component goes to 0, then the field equations tell you that the space component has to, the inverse of the space component, what I called f, has to go to 0 at the same radius. The converse is not true, however. It's possible for f, that's 1 over GRR, 1 over a, to go to 0, while b is still at some positive value. And in fact, there is a solution of this sort which is Z2 symmetric, and you can then make a coordinate change, r minus r0 equals 1/4 rho squared, and obtain the following expression, which in fact is you can view it as a wormhole of a certain fixed radius, depending upon the height here of b as at the place where f hits 0. So this, you can glue this in smoothly, geodesically completely into another copy in another universe and go through the wormhole. And in that case, I would exclude the r less than r0 region from the discussion. So those are the families of solutions that we find here. Now I'm just going to end by making some comments on stability issues. We haven't looked at anything time-dependent, but obviously it's an important question to ask what happens if you take one of these solutions and kick it. Do they fall apart? And also, what does this have to do, for example, with physical large black holes? So, given the purely numerical nature of the new solutions that we've found, it's hard to study this. Well, you can't do it analytically. But what you can do, at least, is study the stability properties of Schwarzschild itself within the higher derivative theory. Now, one of the things that's known about this is in the theory that's relevant to inflation, r plus r squared, the study of normal modes shows that the Schwarzschild solution, in fact, is stable. And this is not surprising, because since that theory is classically equivalent to ordinary Einstein gravity plus a positive energy scalar field. When you include the Weil squared term, the stability situation is different. And I have only been able to find a little bit of literature on this. There's a paper by Brian Witt, not the one that most people know about showing the nonlinear form of the equivalence to a scalar and a gravity, but another paper which addressed the question of stability of Schwarzschild in this theory with the Weil squared term present. And he suggested that there should be a certain figure of merit here, which is the product of the spin 2 mode of the theory, the gravitello mass, times the mass of the Planck hole divided by excuse me, the mass of the black hole time divided by Planck mass squared. And if that quantity is much, much greater than 1, then Schwarzschild should be stable. So that's for large black holes. On the other hand, he suggested that for mu less than or equal to 1, there could be instabilities. Now, actually, in Brian's paper, he did an initial quasi-normal mode analysis, but didn't find an instability. However, there's a more recent paper by a Korean fellow, Y.S. Myung, who says that Brian Witt did not carry out the quasi-normal mode analysis properly. He didn't do it sufficiently completely for non-static analysis. In fact, he does find instability. So Schwarzschild, again, for mu less than something of the order 1, he does find instabilities of Schwarzschild in this higher derivative gravity theory, which are in fact somewhat similar to the Schwarzschild instabilities that have been discussed in massive gravity theories more generally by these papers. So I'm going to pretty much end on this with just raises the possibility of a certain phase structure for black hole solutions in the higher derivative gravity, with perhaps a hierarchy of stabilities involving the Schwarzschild, non-Schwarzschild black holes, and the 2-2 solutions with naked singularities. Just write up some conclusions here. So we found that there are non-Schwarzschild black holes branching off from the Schwarzschild solution at a certain maximum mass, as I gave, depending on the coefficient alpha of the Weil squared term. There are also wormholes, which in the Z2 symmetric case can be traversable smoothly into another universe. And there are also these 2,2 indicial family horizonless solutions, which happen to be the ones that couple properly to distributional shell sources. So that is the family of solutions that one finds in this theory. I again emphasize that these are gravity R plus curvature squared terms occur in essentially every approach to quantum gravity. So providing there's a range of energies in which these are the relevant terms to discuss, one should be thinking about these solutions as well. So thanks for your attention. Yeah, Larry. Yes, I happen to have a couple of slides on that. So, because we have the curvature squared terms in the action, the notion of entropy that one should use is the walled. Oh, what happened? I seem to have. How do we get this back? Ah, this is better. Yes, right. So one should use Bob Wald's proposal for entropy is the integration over the horizon of the variation of the Lagrangian with respect to the curvature. The temperature is given by the usual relation to surface gravity. And in that case, this is now for, let's look at the R and Weil squared theory. Again, with this form of the metric B and 1 over F, we get the following expressions for the temperature and the entropy. The temperature is still given in terms of a nice geometrical quantity. The entropy you have to go and calculate in terms of the details of the A and the B functions. But for the non-Schwarzschildality parameter near Schwarzschild, you see we end up with this expression for the entropy. This delta is the same delta I was talking about before. And then you get the following graph of entropy, walled entropy versus mass. So the solid line here is the new solutions, and the dashed line is Schwarzschild. What you get from the numerical analysis here, the mass and temperature in terms of the entropy, you find that this does still verify approximately the first law of black hole black hole mechanics. So that aspect of thermodynamics seems to be in good order. About the second law and so forth, while we were talking about this over lunch with Faye, I don't know what to say. I don't know if there is a good second law of thermodynamics for these systems. Faye may have some comments on that tomorrow. She was of the opinion, I don't know if Faye is still here, at lunch. You thought that there should be a second law of thermodynamics for this case. Is that a fair quote?
Exactly about your case, I don't know. I mean, what I do know is that for Lovelock black holes, the second law is violated, even at the classical level. So two merging Lovelock black holes don't satisfy the area increase theory, or the, not area increase, but entropy increase law. But I was just looking online, and Aaron Wall has proved that at the linearized level, higher derivative theories do satisfy a generalized second law. It's just when highly nonlinear events like black hole mergers occur that can't be described at the linearized level that there's an apparent violation. But if you restrict yourself to the linear theory, then apparently there is a second law.
That brings to mind, I should say, about stability. There's a point that we were discussing a bit in Gerard's talk. The ghosts, prima facie, look very bad, but there are indications that at least for perturbative excursions away from flat space or other positive energy solutions of the theory, they may not immediately lead to runaways. An example of this is Christodoulou's proof of the stability of flat space in GR, which can be extended to GR plus a scalar. And I have it from Toby Weisman. This even works if you flip the sign of the scalar kinetic term so that you make it a ghost. Still, flat space is stable. And it's basically the dispersive nature of gravity that is causing this to happen. Of course, general relativity with a wrong sign scalar eventually can have instabilities, but they would have to be non-perturbative. So that seems similar to what you were just saying.
Just to follow up on that, in these higher derivative theories, there are certainly cosmological solutions where the de Sitter-like horizon will shrink with time. So violating the generalized second law when you extend it to cosmological as well as black hole horizons.
Right.
It's been known for some years.
Are you referring to Lovelock type gravities? Or I know there's some comments about that for Lovelock.
If you just take these like higher derivative theories and then just take the usual, not the, I don't know with the Wald definition, but just take the usual horizon area definition for the cosmological horizon, then you certainly have solutions where that will decrease with time. And so then that opens the question about whether one wants to use that as a criterion to rule out those theories. Do we, in a general sense, do we say we are so fixated on the second law of thermodynamics that, as Eddington said, any theory that violates it should collapse in deepest humiliation? Should we use it as a criterion for ruling out such theories, or should we only rule out the solutions that have decreasing generalized entropy, and still retain the theory, other solutions in the theory? That's, I think, it's a more philosophical question than a physical question.
There certainly are. I'm quite aware of philosophical debates about this kind of thing. For example, with Cliff Burgess, who is very much involved with effective field theories. And his point of view on effective field theories is you should only consider the solutions of the original second order differential equation with small perturbations and discard everything else. I don't know how to engage in that, because he says he's rather a Taliban on that subject. He wants to insist that this is the way you have to do it. To me, it seems, well, for example, Gerard's proposal, if you're going to have this Weyl squared term because it's renormalizable, then if that's your theory, you should take it seriously and look at what the theory has. You can't, at that point, late point, decide to pick and choose the solutions you like and you don't. You can impose boundary conditions of no rising Yukawas at infinity and so forth. But once you've satisfied those, the theory gives you what it gives you.
So I was worried about positive energy and negative energy states that together have zero energy and therefore should be very easy to produce out of nothing, which would be an indication of the vacuum itself being unstable against production of such a thing. That is, you start with an infinitesimal field configuration that infinitesimally deviates from the vacuum, and then that should blow apart. Because no energy conservation law stops it from growing.
Absolutely.
Did you find any of such phenomena?
No, all I can say is, I refer to these studies of the stability of flat space in theories with ghosts, where even though there are negative kinetic energy terms in the action, nonetheless, flat space can still be stable. So that's the only thing I can
But
really
is it
respond
always
to that.
stable, or are there cases where, for alpha and beta and so on, where you can construct such
I'm not
configurations?
claiming that I know that in this theory. The examples there are general relativity with a wrong sign scalar. Right, so the massive spin 2 ghost is more complicated, and nobody's tried to analyze that. But it's a possibility that the dispersive nature of general relativity is still powerful enough to not allow a runaway to develop in the way that you're suggesting. I should say another person who takes this attitude is André Smilga, who has a series of papers on theories ostensibly with ghosts, but which you can live with.
I see.
And it's basically the same idea, that you don't necessarily excite the runaway solutions just because you have a negative kinetic energy term.
Okay.
I thought it's interesting. There seems to be a black hole that has zero entropy in this theory. So presumably,
Right.
does that have a non-zero temperature at that point?
I think it does, yes.
It does. But so
Well, you just have the equation here, so you have to solve that.
yeah. Okay. Yeah. So it has a. But in any case, then there presumably couldn't be any kind of a microscopic definition of entropy in terms of state counting for this type of black hole, because if its entropy is zero, it could only have one state.
Yes.
And yet it's still a thermodynamic system that radiates.
I mean, maybe one point of view on all of this is that there are enough strange features of these solutions that you decide that you really come to the conclusion that you shouldn't allow this at all, and therefore you consider these, or maybe they're just artifacts of something like string theory expansion, which goes on forever, and yet higher terms remove the unpalatable aspects of these solutions.
But then the other possibility is to add a symmetry such as local conformal symmetry, which could say, yes, all these instabilities do occur, but only in the gauge sectors which are equivalent to the vacuum, so that we won't see anything of this. This would just be a gauge ghost. So if you promote some of those ghosts that we see as being gauge artifacts, then maybe you can get away with it.
Well, except that the spin 2 ghost is not a gauge artifact. I mean, that would affect a scalar. And by the way, the R-squared scalar here is perfectly innocent. It doesn't produce any problems at all. In fact, it's exactly what people want for inflation.
But that, I think, is an example of this, that because you rescale the metric tensor to remove that R-squared term.
Yes. Yes. Well, so there is, at least at the linearized level, a reformulation with an auxiliary field introduced to get rid of the Weil-squared term in favor of a Pauli-Fierz type action with, however, the wrong sign. So you can do similarly, introduce an auxiliary field to to have second-order differential
That's how I
equations.
derived this gravitello,
Yes.
by making this transformation.
Yes, right. Exactly.
I mean, even if one can argue that ghosts are okay classically and they do not destabilize, for example, vacuum, you may still have to radically change your quantization procedure, because even at the level of free field theory, when you quantize and compute a vacuum persistence amplitude, a ghost will give you problem with unitarity. You don't need interactions or curved space-time for that.
I'm not quite sure I've understood the question about, I mean, in what sense do you think you'd be radically changing the quantization
I mean,
procedure?
just compute a path integral for a free field. If you change the sign of the kinetic term,
Oh,
you have an external source J that you couple to it. If you compute this, you will see that you get probabilities which are greater than 1, basically.
yes, that's...
And this is completely free theory, no interaction.
Well, you have a choice. When you have a negative kinetic term, you have a sort of devil's choice between two things you can do. It depends on the I epsilon terms in the propagators.
Yeah.
You choose them one way, you'll get positive norm states in the Hilbert space, but negative energies. Choose them the other way, you'll get negative norm states with positive energies. Either way, it looks bad.
Yes.
And then, of course, then there are other procedures, of course, going back into the 1960s with the Lee-Wick approach to quantization, where you can try to devise specifically tailored inverse Fourier transforms to avoid the ghost poles. There's always a price that you pay for any one of these manipulations. If you follow the Lee-Wick procedure, you'll find that you've lost analyticity of the S matrix. So it always seems to be there's an element of disease in whatever you do here. But there, perhaps one could say that the dynamical ghosts, the actual time evolution ghosts, are you can the idea of asymptotic safety is that you can arrange for, even though they're in the Hilbert space, because of the asymptotic freedom of the theory, you can arrange the coupling to those states to be such that you never excite them as long as you go along the right renormalization group trajectories. In that case, one could contemplate looking at these static solutions, which don't have anything terribly wrong with them, with a situation where you don't actually excite the dynamical ghosts. Okay.